Good morning, class. We are looking at 8.8 vectors. We've already covered polar equations and graphs, the complex plane, De Moivre's theorem, and now we're going to look at vectors. So the objective would be to graph vectors, find a position vector, add and subtract vectors algebraically, find a scalar multiple and the magnitude of a vector, find a unit vector, find a vector from its direction and magnitude, model with vectors. Again, let's look at basic trig identities. We've covered many identities, even and odd properties, a periodic function, unit circle, right triangle, fundamental identities, sine law, cosine law. Then the sum, difference, double angle, and half angle formulas, as you can see here. We moved on to polar coordinates. In short, a pair can be represented as x comma y in a rectangular coordinate system, or r comma theta using polar axis and polar grid. The polar axis in essence is just like the x-axis. The pole is just like the origin. So when we go from x comma y to r comma theta, it is not unique. Because instead of theta, we can say theta plus 2k pi. If we want to represent r as a negative value, we can do so. We just add either pi or odd multiples of pi to theta. Needless to say, when we say 2k pi or sometimes 2n pi, k, n, those are integers. So rectangular versus polar grid. Then we looked at some graphs. When theta is a constant, tangent of that times x gives us y, which is a line through the origin. When r is a number, is a constant, we have a circle centered at the pole or 0, 0 with radius being equal to a. When r cosine theta equals a, since r cosine theta is x, we have a vertical line, x equals a. If r sine theta equals b, that means y equals b, it's a horizontal line. In these cases, where we assume a to be positive, r is 2a cosine theta or minus 2a cosine theta or 2a sine theta or minus 2a sine theta. They are all circles. They all have the same radius a. In the case of cosine, the center is along the x-axis. In the case of a sine, the center is along the y-axis. Then we looked at the complex plane, De Moivre's theorem, a complex number. We have seen it already. We normally called it a plus bi. Now it's the same thing, x plus yi, where x and y are real numbers, just like a and b. I, by definition, is square root of a negative 1, is an imaginary number. The magnitude, also known as modulus of a z, is a distance from the origin to the point x comma y. Calculation that is equal to square root of x squared plus y squared, or r, or z bar, take a square root. Now, I want to make sure everybody understands z bar is the complex conjugate of the z. Here's the z. You can think of it as a plus bi, and z bar is a minus bi. That's the same concept. So let me in fact write that in case. So it's the same idea. So you can think of this as a plus bi and think of this as a minus bi because we are familiar with that in algebra. And so x equals r cosine theta, y equals r sine theta. And normally we go with r being positive, theta being between 0 and 2 pi. So complex numbers can be put in polar forms. Z equals x plus y I, r cosine theta plus I, r sine theta. And the shorthand notation for this would be r cis theta, cis theta. So you have a point here. This distance is r, or the modulus of z, square root of x squared plus y squared. So this is x amount along the real axis, y amount along the imaginary axis. So z is x plus y I, r cosine theta plus I sine theta. R is positive, theta is between 0 and 2 pi. Here's the synopsis of what we have got. Another way of writing this is the Euler equation, r e to the power of I theta. And tan theta is y over x, so that makes theta tan inverse of y over x. You always have to pay attention to the quadrant. If you want to multiply two complex numbers in the form of r cis theta, we multiply their magnitudes, and then the arguments will add up. Cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. If we want to divide one by the other one, we divide their magnitudes, and the difference of their magnitude, their argument, cosine of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. And the Morse theorem says when n is larger than or equal to 1 and you want to raise this to a power, it is easier to raise it to the power using the complex format. You just raise the magnitude to that power, and then the argument gets multiplied by n. So theta becomes n theta. If you want to take a complex root, it's important to know that the nth root, that means there are n individual complex roots. For example, a cube root means there are 3 roots. So when n is larger than or equal to 2, there are n distinct complex nth roots of this number. So how do you find that? You take the nth root of this number and then you put cis. You divide this one by n, cosine of theta 0 over n, and you add 2k pi divided by n. You, of course, simplify that, and then you let k be 0, k be 1, 2, all the way to n minus 1. From 0 to n minus 1, there are n distinct complex nth roots. So that's the synopsis of this section. Let's go to new stuff. Geometric vectors. Vector is a quantity that has both magnitude and direction. Examples: weight versus mass, velocity versus speed. So the idea is, for example, if you say I'm doing 50 miles per hour north, or just 50 miles per hour, whether you include the magnitude or not, it makes a difference. That could be velocity that has magnitude and direction if you include that. Otherwise, just 50 miles per hour, which is simply a scalar, a number. So here's a line that contains 2 points PQ. Here's a line segment that goes from P to Q only. And here's a vector where we start at point P, this is the initial point, and the arrow is the ending point, the terminal point Q. So I want to distinguish between those. This continues indefinitely on both sides. It's a line segment, it's a portion of that. And a line segment that is directed, if you will, directed line segment PQ. So you put a small arrow at top of it. That's how you write it as far as the notation is concerned. Again, initial point, terminal point. Given vector PQ, magnitude is distance from P to Q. Direction is the direction from P to Q, meaning what it makes with the x-axis in essence. So two vectors are equal. V equals PQ, V equals W, if they have the same magnitude and direction. So doesn't matter where they start, where they stop. If they are parallel, that means they have the same direction. And then it covers the same distance. That means they have the same magnitude. You can move it in space anywhere, and they are considered equal vectors. So one more time. They are parallel. That means they are in the same direction. Of course, they could be parallel and going in an opposite direction. Okay, then it makes it negates the vector. That's not what I'm talking about. And they have the same, they cover the same distance, they have the same magnitude. Vector addition is commutative and associative. We take the V and W to be vectors. Alpha and beta represent scalars, meaning some numbers, real numbers. And so we can write if V plus W is the same as W plus V, U plus V plus W is U plus V plus W. This is commutative property. Remember the commutative property of addition, or for that matter, multiplication. And this is associative property of addition or multiplication, in this case for the addition. And we have something called a zero vector. V plus 0 is the same as 0 plus V equals V. And many times, when they want to represent the zero vector, they use this notation rather than just 0, just so you know that. And if you add the vector to its opposite, they add up to a 0, and that's not a regular 0, it's a 0 vector. How do you define the V minus W? I hope you remember in basic math, we also defined the difference in this manner. V plus negative W, which is the opposite of W. So add the opposite of W to V. Properties of scalar products, multiplying vector by number geometrically scalar. So 0 times a vector results in 0. 1 times a vector results in the same vector. Negative a 1 times vector gives us the opposite. If we multiply alpha plus beta times V, we can add them up and multiply by V, or alpha V plus beta V. Alpha times V plus W, you can distribute alpha V plus alpha W, and alpha times beta times V. You can multiply these two numbers in any order. These are two numbers times the vector. So if we look at the graph, and this represents a V, you go with the same direction, same initial and then terminal as far as the side is concerned, and make the magnitude 2 times, it becomes 2V. On the other hand, if you go with the same magnitude and go in the opposite direction, then it makes it minus V, or the opposite of the V vector. Adding vectors geometrically. Well, there are two ways of adding, and one of them is using triangular method, one of them is using parallelogram. So we want to add V and W. We start with the initial point of V, and the terminal point of V connects to the initial point of W. And now V plus W starts from the initial point of V to the terminal point of W. V plus W. This is a triangular format, triangle. If you want to go with the parallelogram, V and W, if you want to change it to a triangle, you can write this one is parallel to V, and therefore with the same direction and same magnitude, it's the same as V. And you follow the triangular method, and that's the answer. And since this is the same answer, you can say, well, if I want to add these two, I just draw a parallelogram, and the diagonal is the answer. So one more time. If it's in this format, it's ready to go, you have the answer. If it's in this format, you can go and use the triangular method, or you can say, I'm going to draw a parallelogram. Diagonal is the answer. So commutative V plus W is the same as W plus V. Associative U plus V plus W can be added in any order. I can add U and V first, or I can add together, or I can add V and W together. So this illustrates that. So take a look at this one. So we start with the U here. We connect it to the V. This is the terminal point of U, the initial point of V. We end up here, and that's U plus V. And then we add the W. This is the initial point of W. This is the terminal point, and the red one is the answer. U plus V plus W. Or we may use U plus now V plus W. So take a look at V and W. So here's V, here's W, and here's V plus W. And so again, you get to the same answer. Opposite vectors, V plus 0 is 0 plus V equals V. That's a 0 vector. V plus negative V, they add up to a 0 vector, meaning if this is V, negative V has the same magnitude in a opposite direction. The difference V minus W has been defined as V plus negative W. So how do we do that? So if this is V and this is W, how do we write V minus W? We draw the V here. Here's the W. Here's the opposite of that, simply because they are identical in magnitude, but a different direction. And so now we see the answer V minus W. In other words, if we go back to this concept of a parallelogram, when we have a V and W, it creates two diagonals. This is the sum, this is the difference. So in other words, if you want V minus W using the parallelogram, So V minus W start with the terminal point of W and connect it to the terminal point of V. So this diagonal is the sum. This diagonal is the difference between the two vectors. Very straightforward, everybody. We are given the V vector, W vector, U vector, and we want to do some operations. The first one being V minus W. So let's see how we do that. Here's the W. So minus W is going that way. So we're going to go this way. Same direction, same magnitude, opposite direction. That would be V minus W. Two V, so this is V, 2V plus 3W, this is V. 2V, we're going to continue until the magnitude is 2 times this. So somewhere here, again, this is not too scary, just to give you an, so you go up until the magnitude of what you make up is 2 times the magnitude of V. And W, you first of all move it here, and then you make it 3 times the magnitude. So you move this here, and you make it 3 times the magnitude. And you connect it. So V multiplied by 2, W move it here and multiply by 3, and this is their sum. Two V, well, we already have 2V, if you will, in essence. Minus W, we already have minus W. You can think of it as you want minus W, so you put it here. You see this one, you put it here. So if you move this here, and then you move it there. Just to give you an idea, let's just show that, and we're gonna, so this is 2V. This is minus W. And this is U, and you connect these two. Looking like this. Maybe clean up the mess. So 2V, W in the opposite direction, same size, same magnitude. This is U. We are assuming, because this may not be to scale. And then this is 2V minus W plus U. Okay. Magnitudes of vectors or modulus, it shows that almost like an absolute value, but there are 2 lines, and it's also called norm. To compute the magnitude is the notation and direction of a vector. An algebraic way of representing vectors is needed. So let's discuss position vector V. If a V equals A comma B, this is the notation that is used for a comma b is an algebraic vector whose initial point is at the origin, then v is called a position vector. So in short, what is a position vector? Whatever vector you have, you move it such that the initial point is at the origin. So the distance to that terminal point is the magnitude, and this is the direction, this angle, theta. Again, counterclockwise is positive. So that's a position vector. Algebraic vectors, v is represented in this format, or ai plus bj. A and b are called components of the vector v. I along the x-axis, j along the y-axis. Magnitude of a vector is calculated just like the r square root of a squared plus b squared. Magnitude is a number and it must be greater than or equal to 0. Can it be 0? Yes, for a zero vector, otherwise it has to be positive. If the magnitude is 0, then you have a zero vector, v equals 0. Two vectors that are opposite of each other, they have the same magnitude. So the magnitude of minus v and v must be the same. If a number, an absolute value of any number gets multiplied by the magnitude of vector, it gets larger by that much. So the magnitude of a times v, a is a scalar, is the same as multiplication of the absolute value of a times v. For example, let's say we are looking at 5v, that would be 5 times the magnitude of v. Let's say it's minus 5v. And the reason we have an absolute value, because even in the case of a minus 5v, the magnitude is the same as 5v. We also define a unit vector. A unit vector is a vector whose magnitude is 1. Any vector whose magnitude is 1. So let me actually spell it out. Magnitude. Any vector with the magnitude of 1 is called a unit vector. Let's continue with this position vector. A vector with initial and terminal points x sub 1, y sub 1 for p, and q is x sub 2, y sub 2 is equal to the position vector v equals pq, x sub 2 minus x sub 1, y sub 2 minus y sub 1. This puts it at the origin, the initial point. Or the vector p1, p2 is a comma b equals x sub 2 minus x sub 1 comma y sub 2 minus y sub 1. We may use pq, we may use p1, p2, a couple of different points. And so if we look at this case, p1, p2 is somewhere in this space, having the coordinates x sub 1 and y sub 1 for p1 and x sub 2 and y sub 2 for p sub 2. If we write, and this distance is x sub 2 minus x sub 1, so if we go with x sub 2 minus x sub 1 and y sub 2 minus y sub 1, we can start from here, and this distance a must be identical to this distance x sub 2 minus x sub 1, and this distance b must be identical to this distance y sub 2 minus y sub 1. In other words, just basically move this such that the initial point, namely P sub 1, is at the origin. Now this is called the position vector. So here's the position vector AB. Remember, the origin is at 0, 0, so A minus 0, B minus 0. So OP has the same coordinates as just P. We want to find the position vector of the vector V equals P1, P2 if P1 is negative 1, comma 2, and P2 is at 4, 6, using this. So we subtract their x's, we subtract their y's in a proper order. Which order? We subtract the first one from the second one. So that means 4 minus 1, 6 minus 2. That's how we do it in the proper order. The first one from the second one. Okay, so we have first, this is the point, negative 1, comma 2, you locate that. This is 4, comma 6, you locate that. And this is a P1, P2. And let's find the position vector using the formula. So 4 minus negative 1, 6 minus 2. This gives you plus 1, making it 5. And this makes it 4. So 5, comma 4. So all you have to do, go 5 to the right, 4 up, and draw. And this is an equal vector, but it's a position vector, meaning the initial point is located at the origin. Two vectors are equal if their corresponding components are equal, as we know it already. Again, reminding you of the position vector. If V has coordinates A sub 1 and B sub 1, and W has coordinates A sub 2 and B sub 2, and if they are equal, then A1 must be equal to A2 and B1 must be equal to B2. So if we are claiming two vectors are equal, their components must be identical, must be equal. Unit vectors I and J. V, which is represented by AB, this is the vector AB, is equal to A times 1, 0 plus B times 0, 1, or AI plus BJ. These are different representation of the same vector. In which case, this is I, this is J, and those are unit vectors. So what is this one along the x-axis? What is this one along the y-axis? So one along the x-axis is the I vector, and one along the y-axis is the J vector. So take a look. This is considered I, 1, comma 0. This is considered 0, 1. So how many of this we have, how many of that we have, and we put them together. Let's look at finding another position vector where we are given two pairs P and Q. Remember, the position vector V is x up to minus x sub 1, and y sub 2 minus y sub 1. So subtract the first from the second one. So this would be 4 minus 4, and this would be 6 minus 9. This results in 0. This results in negative 3. And you can say it's negative 3j because if you go with this format, A is 0, everybody. A is 0, and B is -3. So again, different ways of representing a vector. Find a vector from its direction and magnitude. And again, this is one way to represent a vector. So let's start. A unit vector in the direction of a V is found by dividing the V vector, its components, if you will, by its magnitude. Finding a vector from its direction and magnitude, if we have the magnitude of the vector, that means we have this value. And if we have the direction, that means we have the value of alpha. So what is given? The magnitude and the alpha. This is how you find the vector. So it's the magnitude times cosine alpha I plus sine alpha j. So the magnitude, reminding everybody that it's square root of a squared plus b squared. The unit vector in the direction of v is v divided by the magnitude. And therefore, if you want to find v, it's the product of these two. Right? Take a look at the cross product. V is the magnitude of v times the u, the unit vector. Now, find the vector v whose magnitude is 7. This is 7. And whose component in the I direction is both positive and equal to the component in the j direction. Which means A equals B. And the magnitude square root of a squared plus b squared equals 7. So that's what we are looking to solve, everybody. Well, A is equal to B. So we have 2a squared equals 7. Sorry, it's 49. So a squared equals 49 over 2. A is plus minus the square root of 49 over 2, or plus minus 7 over the square root of 2. And I can multiply by square root of 2 over 2. I get plus minus 7 square root of 2. This is square root of 2 over 2. So there are two answers. Positive only. So this is 49. And that's what we get. And again, there are two answers. There are two answers, but we keep the positive only. So just bring this down a little bit because of our writing here. So those are the answers. And again, just this is 49. Okay. And two answers, positive results in this. So you put it in the format that they ask. V is 7 square root of 2 over 2i plus 7 square root of 2 over 2j. That's the answer. All right, add and subtract vectors algebraically, vector properties of addition, and scalar products. If a V is A1I plus B1J, we can represent it in this format or in this format. W is A sub 2I plus B sub 2J in this format or in that format. And alpha is a number, is a real number, is a scalar. Let's see what happens. Now, V plus W, we just add these two. And A plus 1 times A plus 2 times I, P plus B1 plus B2 times J, or in this format. And if you want to do the subtraction, this becomes negative. So here's the V with components A sub 1 and B sub 1. Here's W with the components of A sub 2 and B sub 2. So we draw W here where we have the terminal point of V parallel to that. And for this distance is A sub 2, right? And this distance is B sub 2, right? Remember, this was B sub 2, now it's shifted up. And therefore, the resultant, the sum, which ends here from the initial point of V to the terminal point of W, has coordinates A sub 1 plus A sub 2, B sub 1 plus B sub 2. And that's what we are seeing here. Alpha times V. So if this is V, we multiply everything by alpha. So multiply everything by alpha. Remember, alpha is just a scalar, is a real number. So here's the v vector with coordinates a sub 1, b sub 1. When you multiply it by alpha, everything gets stretched by a factor of alpha. So this is alpha a sub 1 along the x-axis, alpha b sub 1 along the y-axis. Scalar multiplication. The magnitude, again, by definition, is square root of a1 squared plus b1 squared under the radical. And so if this is p1 and this is a sub 1, this is b sub 1, and p sub 1 having coordinates a sub 1, b sub 1, then according to this, the magnitude is the distance from O to P1. And the distance you can use basically the distance formula. X sub 2 minus x sub 1 squared, that means a sub 1 minus 0 squared, plus y sub 2 b sub 1 minus y sub 1 squared. Again, I'm going to remind you, I think everybody knows that. So this is from the distance formula. The square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. We want to add and subtract vectors algebraically. If v is negative 3i plus 4j and w is 2i minus 5j, what is v plus w? Just add them up and add up the components. So we are going to add those two. These two will give us negative I minus j. So again, just in case, these two, and then these two. V minus W, let's write them. Let's distribute. This becomes minus 2i plus 5j. These two add up to minus 5i. And these two add up to 9j. Minus 5i plus 9j. Minus 5i plus 9j. Let's get one more example. Unit vector is the v vector divided by its magnitude. And the magnitude is defined as the square root of a1 squared plus b1 squared, where the coordinates are a1 and b1. V is the magnitude times the u. We are repeating that concept, and the unit vector is a vector with the magnitude being 1. Now, in this example, find a unit vector in the same direction for the vector v equals negative 3i plus 4j. In short, we are looking for this. In order to find this, all we have to do, find its magnitude and divide the vector by it. So let's find the magnitude using this formula. A1 or A simply is -3. B1 or B is +4. Plug in. As you know, this is 9, this is 16. They add up to 25, and the answer is 5. We divide the original vector V by this number. So we get -3/5i plus 4/5 times j, and this is the unit vector. It is always a good practice to prove we have it right. And to prove we have it right, you have to calculate the magnitude of this vector and show that it's 1. So basically, let's raise this to the second power, raise this one to the second power. If you add it, must become 1, and then square that 1 is 1. So this, when you raise it to the second power, becomes 9/25. 4/5. When you square it, becomes 16/25. And that's 25/25, which is 1. Square that 1 is 1. And that's a proof we have found the unit vector.